Hello, Integrated Math 1. Welcome to lesson 3.1.2b. We're still comparing our exponential functions. Last time we got really good at writing our exponential functions. If you know the y-intercept, you know the constant ratio, you can write the exponential function. We're just going to push it a little bit further now, and we're going to compare functions. We're going to solve exponential equations using common bases, all of that good stuff. So to give you an idea of what we're going for here, we're on page 27, by the way, M3-27. So suppose a population of rabbits triples every year. And the table here shows their numbers, right? At 0 years, we start off all of this with 2 little rabbits. After 1 year, we have 6 rabbits. 2 years, we have 18 rabbits. And after 3 years, we have 54 rabbits. So using what you know about your exponential functions, that whole what's the y-intercept, what's the constant ratio, please go ahead and write a function f to represent our rabbit population over time. Hit pause, write it out, hit play to check your work. So first of all, the y-intercept, we know that, of course, let me bring out my pen here. We know that the y-intercept is where x equals 0, so it looks like my y-intercept is going to be 2. So f of x equals 2 times b to the x power, where b is our constant ratio. And they kind of told us, right? I mean, in the actual problem itself, they told us that it triples every year. So of course, my pattern is that we're multiplying by 3. So that means my constant ratio is 3. So I'm going to say that's 3 to the x power. So I have f of x equals 2 times 3 to the x power. Yay, we wrote our function. You probably did that faster than I did. Now that you have the equation, I would like you to grab a calculator. Oh my gosh, grab a calculator. Please don't try to do these. Oh, please don't try to do these in your head. It gets really rough. I would like you to use this function to go ahead and evaluate the population of rabbits for each year. So 10 years, 20 years, 30 years. I only have part A on my screen, but you probably have all 3 parts on your paper on page 27. So go ahead, hit pause, plug in the number, use your calculator, see what you get, and then hit play when you're ready to check your work. So f of 10 means that we're going to do 2 times 3 to the x power, only we're going to do 2 times 3 to the 10 power. Please remember your order of operations means you have to do exponents first. So I grabbed my calculator and I did 3 to the 10 power. I got 59,049 multiplied by 2, and I got 118,098. So theoretically, in 10 years, we would have 118,098 rabbits. That's a lot of rabbits. What about after 20 years? So f of 20 means I'm going to go 2 times 3 to the 20th power. Again, use my calculator. 3 to the 20th power, so big. 3,486,784,401. I am going to multiply that by 2. And I found out that after 20 years, there's going to be 6,973,568,802 rabbits. That's a lot of rabbits. But what about after 30 years? So 30 years means I'm going to go 2 times 3 to the 30th power. You know, I found actually using the calculator on my phone worked better for this one because the calculator on my little screen wasn't quite long enough. So I used the calculator on my phone to do 3 to the 30th power. I had a longer screen. And so I got, oh my gosh, okay, so I have 205,891,132,094,649. Multiply it by 2. And I have 411,782,264,189,298 rabbits after 30 years. That's a lot of rabbits. You know, this is all fine and good, like if I know how many years it's been and then I want to plug in and figure out how many rabbits I have. But what if I wanted to go backwards? What if I wanted to know when I would have a certain number of rabbits? Turns out you can go backwards. Of course you can. You knew you could. Like, how long would it take for my population of rabbits to reach 4,374? So they have this all worked out here on your paper on page 27, but I'm going to work it out off to the side just so you can see what I'm thinking here. So I have 4,374, and I want to know when that's going to equal 2 times 3 to the x power. I want to know when I'll have this many rabbits. So I'm going to solve it. In order to get x alone, the first thing I need to do is actually divide by 2. So I will divide by 2, and again, calculator, super useful. If I divide that by 2, I get 2,187 equals, oh, the 2's cancel out, equals 3 to the x power. Now, here's the thing. If I'm trying to find x, I'm trying to figure out 3 to what power would equal 2,187. So I'm trying to figure out, right, like what goes there. So you know what? I played with this a little bit, and you may have to just play with it with your calculator a little bit. And I realized that if I did 3 times 3 times 3 times 3 times 3 times 3 times 3, then I would get 2,187. So I realized that this is 3 to the 7th power would equal 3 to the x power. Well, because I have the same base on both sides, in fact, I'm going to write that a little better. Hang on, I'll just clean that up just a little bit. Pew, pew, pew. Because we have the same base here, that means my powers should also be equal to each other. So 7 equals x. Oh, look. So it's going to take 7 years for the rabbits to reach a population of 4,374. All right. That's doable. We're actually going to skip this next problem. I don't like it very much. I meant to take it out and I forgot. So there it is. If you're dying to see it, you can hit pause and check it out. Let's go over to number 4 on page 28. I have a couple of these. I only have one at a time on my screen, so I only have A up right now. But on number 4, you should have A, B, C, and D. I believe you have 4 of these. I'll have to double check that. Go ahead and work out all of the problems on number 4. Solve each equation for x. Start by trying to get your bases to match. That's the goal, right? Get your bases to match, and then your exponents should be equal to each other. So go ahead, hit pause, see what you can do working these out, and then hit play when you're ready to check your work on all of them. So here I have 3 to the x power, and I thought, I could rewrite that 81 with a base of 3. And I realized 3 times 3 is 9, times another 3 is 27, times another 3 is 81. Oh, look at that. So 3 to the 4th power it shall be, because 81 can be rewritten as 3 to the 4th power. My bases are now the same, so I can say that x equals 4. Yay. If we do the next problem. This one got a little trickier. 2 to the 4x power equals 1. Now, I'm not worried about that 4x. I mean, I will worry about it, but not right now. I want to make sure my 1 has a base of 2. And I had to give this a little thought, but I realized anything to the 0 power is 1, right? So I rewrote this as 2 to the 0 power. So I have a base of 2, a base of 2, and that means then that 4x has to equal 0. And even if I divide both sides by 4, well, 0 divided by 4 is still going to be 0. So we get an answer of x equals 0. Yay. They got trickier though, right? They got trickier. So I was looking at this one and my thought was, okay, I need a base of 4. And I thought, well, I can rewrite 64, right? 4 times 4 is 16, times another 4 is 64. Okay, so I rewrote that 64 as 4 to the 3rd power. But I realized I had another problem because these didn't quite match, right? This was in the numerator, this was in the denominator. Don't want that. So I rewrote this. Are you watching? Remember our boot camp from earlier? I rewrote this as 4 to the negative 3 power. And now that I have this written as 4 to the negative 3 power, my bases match. I have a 4, I have a 4. And now I have 8 minus x equals negative 3. So great, I'm going to get my x alone. That is a positive x. So I went ahead and subtracted 8 on both sides. Pew. Those cancel out. And I now have negative x equals negative 11. And I went ahead and divided both sides by a negative 1. Pew, pew, because I don't want negative x, I just want x. So the negatives canceled out. Negative divided by negative is a positive. Negative divided by negative is a positive. We got x equals 11. Yay. Well, just a little bit more. Just a little bit more. 5 to the 9x equals 1. Hopefully you recognize this is the same trick from earlier. Yeah, I can because anything to the 0 power is 1. So I can rewrite this as 5 to the 0 power. Now my bases match. So I can say 9x equals 0. I can divide both sides by 9. Those cancel out. And of course, 0 divided by 9 is still 0. So we found our answer as x equals 0. There is a little bit more. Ooh. There were a few things wrong here. So first of all, I was like, okay, that 243, I'd like to rewrite it. But before I do, the fraction's freaking me out a little bit. So I rewrote this with a negative in front of my exponent. Do you see that? 3 to the negative x plus 5. Once again, I'm going to point out, as so often happens, this is not the only way of solving this. This is a way of solving this. Please remember that. I rewrote that 243. Let's see, 3 times 3 is 9, times 3 is, because I want a base of 3, 81, times another 3. Oh, 81 times 3, that's 243. And again, feel free to use your calculator to help you out. So I have 3 to the 5th power, is that right? Yeah, 3 times 3 times 3 times 3. Oh no, times 3. Oh, that should be a 4, not a 5. Badness, Scott. It's a 4. So I'm going to rewrite this as 3 to the 4th power. No, it's not. It's 3 to the 5th power. Just kidding. See, the joy of these videos is you get to watch me make my mistakes. 3 to the 4th power is 81. 3 to the 5th power. Okay, 3 times 3 is 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. All right, it's a 5. We're good. And now that my bases match, I can, of course, say that my exponent should also match. There are a few ways of doing this. You could distribute the negative if you wanted to. But you know what I did? Do you know what I did? I divided by a -1 on both sides. And I was like, that'll fix the problem. So these negatives cancel each other out. 5 divided by -1 is -5. And now I can subtract 5 from both sides. Those cancel. -5 and a -5 is a -10. And I'm like, x equals -10. Yay. One more. Just one more. I'd like you to solve this equation for x. So I looked at this one and I was like, well, 2 to the -x power. And I was like, well, I sort of have a base of 2. In fact, I could say that's 2 to the 1 power, right? But again, I want the bases to match exactly. I don't want like one on top, one on the bottom. I want them to match exactly. So I'm going to rewrite this with a negative exponent. I'm going to say that's 2 to the -1 power. And now that my bases match, I can say negative x equals -1. I can divide both sides by a -1. And negative divided by negative gives us positive. So I have x equals 1. Yay. So this just takes some practice, like just playing around with it a bit. All right, now that you're experts on solving these equations for x, let's compare some functions, shall we? Page 29, I have 2 exponential functions in each pair, all right? So I've got a couple of these. Each pair, you've got 2 exponential functions. You might have a table and a graph or 2 tables, but we're gonna compare, actually, I think all of these have a table and a graph. I would like you to compare the 2 and answer each question for all of them, all right? So start with number 1. We have questions, I think A, B, and C. Go ahead, hit pause, answer the questions, hit play when you're ready to check your work. All right, so y-intercept, right? I'm looking for that y-intercept. So I'm looking for where x equals 0. So it looks like the y-intercept for function A is 1. And then I was looking at this one and I can see my y-intercept is right there. And I was kind of looking, if that's 5, it looks like it's not the best graph, but it looks like my y-intercept here is also hits my y-axis at 1. So which function has the greater y-intercept? Neither. They have the same y-intercept. They both have a y-intercept of 1. So I guess we didn't have one that was greater than the other. Now, constant multiplier, it might be easier if you think of it as your constant ratio, right? That might be a little easier to think of it. So I'm looking at your pattern from here to here to here. It looks like we're multiplying by 4. So I'm going to, oh, sorry, that 4 is like tiny. So I'm going to say that my constant ratio is 4. For this one, it was a little trickier, but I decided if that's at 0, 1, right, we've got 0, 1. Actually, hang on, I'm going to write that further up because I know it's about to be in the way. So this is 0 and then 1, right? That's what we have here. Where would my next point be? Well, I'm going to go over 1 and up 1. And it's a little bit higher. In fact, it looks like it's about twice as high as where we were before. So I would say that my next point is at 1, 2. So it looks like to get from here to here, I have to multiply by 2. So I'm going to say that my constant ratio is 2. That means if function A is a constant ratio of 4, function B is a constant ratio of 2, function A has the greater constant ratio, doesn't it? Awesome. Question number 2, we have some similar questions, only now I've got a function and a graph. Go ahead and hit pause, answer the questions that we have there for you, and then hit play when you're ready to check your work. All right, let's talk. Which function is the greater b value? Remember that the b value is your constant ratio. Don't forget that. So if you've forgotten that, that'll help. So b value is the constant ratio. Well, this one's pretty easy. My b value is 3, right? There it is. Constant ratio. So it looks like we're still at, again, I find to find that constant ratio, it helps to just kind of like pick some points. So it looks like my y-intercept is at 0, 1 again. But look how this one's steeper. So if I go over 1, I actually end up like all the way up here at like 5, don't I? So my next point is at 1, 5. So to get from here to here, looks like we have to multiply by 5. So I would say my b value is 5. So function b has a greater b value. Horizontal asymptote. Ooh, well, you don't have to do this, but if you wanted to make like a little table and you're like, I know if I plug in a 0, I get 2, right? We know that the pattern is that we're multiplying by 3. So you'd be like, so I'm just going to put a few points in here just to kind of help me see what's going on. So if I multiply, let's see, 2 times 3 is 6. Times 3 is 18, times 3 is 27. You know what, though? That's going bigger. That doesn't tell me where it's going as far as the horizontal asymptote goes. So maybe, hang on. Maybe I'm going to work my way backwards. Right? So if I have at 0, I have 2. And instead of multiplying by 3, let's divide by 3. So at -1, if I divide by 3, that would be 2/3. Sorry, my 2 went weird. Next up, if I divide by 3 again, that would be 2/9. If I divide by 3 again, that puts me at 2/27. Oh my gosh, that's getting really small. It's heading towards 0, isn't it? Oh, so my horizontal asymptote is at y equals 0. And I don't even need a table. I can see it swooping down and it's heading towards 0. Do you see that? So I'm going to say my horizontal asymptote here is also y equals 0. So both functions have a horizontal asymptote at y equals 0. Yay. Number 3, 2 more questions. Function A, function B. Go ahead, hit pause, answer these lovely questions, and then hit play when you're ready to check your work. All right. This guy right here, -2. We're asking for the y-intercept this time, right? The y-intercept. Well, I can see my y-intercept is -2, so that's easy. I can see on this one, if that's 0, looks like my y-intercept is 81. Wow. I'm going to say function B has the greater y-intercept as a y-intercept of 81. So I think it wins that competition. Ooh, which function decreases across its domain? Okay. This means when we're saying decreasing, that we're saying as x, let me write this a little bit better. Let me erase that. So what we're saying by decreasing, we're saying as x gets bigger, that means that y gets smaller. I can't even. Hang on, I'll fix it. Y gets smaller. Okay, so make a little note of that. All right, so as x gets bigger, y gets smaller. So let's just do a few numbers here, Here I have -2. Oh, actually, I'm going to try that again. My y-intercept is -2. So that means if I plug in a 0, I should get out a -2. Yay. My pattern is to multiply by 3. So if I times by 3, that's -6. Times by 3, that's -18. There we go. Sorry, guys. And if I multiply by 3 again, I find myself at -54. Wow. Yeah, that's definitely getting more and more negative. It's definitely going down, isn't it? My y is getting more and more negative, more smaller. So this function is definitely decreasing. All right. Let's look at what's going on the table. The table's a little easier to see, which is why I made a table here. As x gets bigger, oh, sure enough, as x gets bigger, this function's getting smaller and smaller, isn't it? So I'm going to say that function b is also a decreasing function. As x gets bigger, y is getting smaller. So turns out they're both decreasing functions. Hang on, I'm going to erase all that so you can see the pretty writing. Yeah, so both functions are decreasing across their domains. Sweet. As always, I hope you found this helpful. I hope you found this useful. If you got questions or concerns, let me know, and I'll see you guys soon. Bye.